Almost an year ago, I saw this video, which is about the 4 dogs problem. The problem is this. 4 dogs represented by A, B, C, and D are located at 0, 0, 1, 0, 0, 1, and 1, 1 respectively. If each dog always heads towards the next dog at 1 unit per second, so A follows B, B follows C, and so forth, then what would be the paths that the dogs take? The eventual solution in that video is quite different from my problem and the solution I get to, but the video is very intuitive overall, and it'd be great for you guys to check it out sometime. Before finishing the rest of the video, I opted to try solving it myself. My main approach was with calculus, setting the path as a parametric function and trying to use rotational symmetry relations for differential equations. This, however, didn't really work out. I didn't really have much experience with differential equations that have 2 different functions in the first place. Stumped by the problem, I thought of a simpler, or what I thought would be simpler, version of the dog problem, where the path of one of the dogs is given. The problem is this. Dog 1 starts off at 1, 0 and moves upwards at 1 unit per second, and dog 2 starts out at the origin, again moving at 1 unit per second but always heading towards dog 1. Then what should be the path of dog 2? It was only in mid-April this year when I finally found the solution to the dog problem, when I doubted that there was an accessible answer to the problem. In this video, I'll be talking about my failed attempts and how I found the answer. If you want to, you can try the problem yourself. Maybe some of you with more experience or knowledge in math can find a better solution to it, which I wouldn't mind reading about. Much like my attempt at the 4 dogs problem, I decided to try using a parametric function to represent the path of the second dog. Then I started writing out the equations: the constant velocity of 1, the initial conditions, and finally differential equations about the directions. The logic behind the differential equation is as follows. For any t at v of t, the velocity vector points the same direction as the vector from v of t to 1, t. So the slope represented by the velocity vector is the same as the slope between the 2 dogs. This differential equation was what I spent the most time trying to solve. With all the multiplication between p of t and q of t, I tried 3 different methods to try to integrate the equation somehow with my limited experience in differential equations. Seeing the terms p prime of t times q of t and p of t times q prime of t, I thought that arranging the terms for the product rule or quotient rule perhaps will work. Since if I move p prime of t times q of t and p of t times q prime of t to the same side, they have opposite signs, I first tried to use the quotient rule backwards. This brings us to this equation. On the right side, this part is easy enough for integrating, but there aren't really any good methods for this part. I couldn't really get past the integration for that part of the equation, so I tried using the product rule backwards next. The result is this equation. The nasty product is still there though. The right side is easy, but the left side is much more complicated. Even if the left side is grouped by p prime of t, it doesn't do anything to help. P prime of t times q of t doesn't have a nice integral. Finally, I decided to try dividing by p of t times q of t, hoping that maybe it might yield something. It works nicely with p prime of t times q of t and p of t times q prime of t, which is what I intended to do. However, it again doesn't work out well with the other terms. For a long time, I went back and forth with the differential equation, never really getting far. I ended up drifting away from the problem for many months. When I came back to the problem during spring, I noted that the main reason I wasn't able to solve the differential equation was because there was multiplication between p of t and q of t involved. I decided that this might hopefully be mitigated by getting an easier equation to solve. Instead of cross-multiplying, I instead came up with this equation. At the time, I thought this will improve things a lot since p and q are separated now. This was true, but this equation also had a crucial part that would impact me a lot later. Using the given initial conditions, I got to solving the differential equations. The results for p and q are these. There are still two parameters left, c and c sub 3. These can be solved with this equation, the equation expressing the speed of 1. However, when the derivatives are plugged in, there is no solution for c and c sub 3. For some time, I was puzzled by the result. Then I realized something. The problem is c. The first differential equation is correct logically, but I failed to account for the fact that c isn't a guaranteed constant. After all, there is no condition that c, the ratio between the magnitude of the velocity vector and the magnitude of the positional difference, is a fixed value for any given time. As a matter of fact, this should intuitively make sense. The velocity vector always has a magnitude of 1, but the positional difference vector should experience change over time. In other words, c is a function of time, c of t. In correcting this error, however, I realized that this is essentially the very first attempt. C of t can be eliminated by algebraic manipulation, and the result is the same differential equation that I had tried to avoid. The results of this attempt in some ways disappointed me. It seemed that the problem perhaps did not have an explicit solution in the first place. With many failed attempts and dead ends, I was getting quite desperate with the problem and stopped thinking about it for even more. After deciding to tinker around with the problem once more, I tried a different approach. This time, I just used f of x to describe the path. I had actually done this a couple of times before, but there were two reasons that I didn't go further with it. First, when I was still thinking of this problem as a scaffold for the original 4-dogs problem, I thought it would be better to do a parametric function since the path in the 4-dogs problem cannot be expressed as a function. Second, the differential equation that I got from it wasn't obvious to solve either. I got to figuring out the properties of this function. It would be defined for x values from 0 to 1, inclusive with 0 but asymptotic towards 1. Using the initial conditions, f of 0 is equal to 0, and the derivative of f at 0 is also 0, since dog 2 would start out horizontally. Finally, for the differential equation, I used the following logic. On some point of f of x, say x comma f of x, the tangent line to f should intersect with x equals 1 at a point, dog 1's location. The y-coordinate of this point should be the arc length of f of x from 0 to x. In other words, at any point, the arc length from 0 to that point determines where the tangent line at that point crosses. How much the dog has traveled, which is proportional to how much time the dog has traveled for, correlates to where the dog is going towards, matching what the problem poses. Translating this logic into an equation yields this. When dog 2's x-coordinate is x, the left side is the distance dog 1 has traveled, and the right side is the distance dog 2 has traveled, both of which are equal since the two dogs have the same speed. This is still a very intimidating equation to work with. Differentiating both sides is inevitable because of the nasty square root inside the integral. Doing that actually helps us a bit since f prime of x cancels out on the left side. However, in previous attempts, I had to give up at this part. I didn't really know what to do afterwards. I tried squaring both sides to get rid of the square root, but that didn't result in much. This time I was willing to try bolder options. Instead of squaring the equation, I moved the terms around differently, isolating all the derivatives of f to the left side. In the past, I probably wouldn't have done this because of the denominator, but I learned some more techniques recently and was willing to try them out. Now, this was an equation that I could handle better. Integrating was a sensible step to take next. The left side has a kind of clear chain rule mechanism going on, and the right side is easy to integrate. The left side was what worried me, which becomes clear when substitution is used. For me, this was an integral that I had never solved before, but I had methods I wanted to try. In the past few months, I had learned about the derivatives of inverse trigonometric functions, and while none of them perfectly matches the integrand, I had some ideas. Seeing the 1 plus x squared inside the square root, I thought of perhaps using arctangent of x. However, I realized that probably wouldn't work very well anyways because of the square root. After some more thinking, I settled on using arcsine of x, even though it is 1 plus x squared inside the square root for the integral we want, and 1 minus x squared for arcsine of x. I took the choice of using arcsine of ix to fix this. I was quite uncertain and uncomfortable doing this since I had very little experience with using I in calculus, let alone an arcsine of x, another thing I hadn't used much in the past. Nonetheless, this cleared out a big obstacle in the problem. I was now able to integrate the differential equation. Integration ends up with a bunch of i's everywhere, but those actually become helpful later on. First off, plugging in t equals 0 means the integration constant is 0. The equation has to be integrated again because of the derivative inside. We simply get rid of the arcsine by applying sine, who would have known, after moving the I at the bottom away. All the i's floating around mean that we can actually use a fun identity. The one between sine of x and the hyperbolic sine or shine of x. If we write both of them out, the sine of x formula coming from Euler's formula, then as shown, they have quite similar forms. Back in the equation, there's a negative I in the sign on the right, so we can follow that to make our identity. Plugging in negative ix in sine of x results in this, which is just shine of x over I. Once the right side is calculated, f prime t can be isolated further by getting rid of the I multiplied to it. This actually completely gets rid of all the nasty i's in the equation, which I was very happy to see when solving it. Even better, since there is a logarithm inside the shine, we can simplify the equation by plugging in the definition for shine of x. After simplifying, we get to a very manageable equation. Integrating one final time and plugging in 0, 0 yields us a solution. Before graphing it, we can try plugging the solution back to the differential equation to check. Calculating f prime of t and f double prime of t, plugging them back in, and finally simplifying. The equation does work out, so we can move on. Finally, we can graph the solution. Something cool is that the graph extends over to negative x values. This would be the path if dog 1 and 2's movements are all switched, if they go the opposite directions of what we had initially, and dog 2 constantly moves away from dog 1. Another interesting thing is that if we see the distance between a given point for dog 2 and the corresponding point for dog 1, it converges to 1/2 as x approaches 1. Pretty cool in my opinion. 1/2 isn't too out of place since if dog 1 heads directly away from dog 2, the distance would be 1, and the distance would be 0 if dog 1 heads directly towards dog 2. A small bonus problem stemming from the dog problem I thought of was this. What if dog 2 was a little bit faster, or a bit slower than dog 1? Seeing the ratio between dog 2's speed and dog 1's speed as a, we get a differential equation very similar to the one for the original dog problem. Solving it carefully yields this equation. A can't be 1, since that would mean that there will be a logarithm rather than the powers inside the equation. It can be other values, however. If A is greater than 1, or dog2 is faster than dog1, then dog2 should eventually catch up. If dog1 is slower than dog2, however, dog1 should eventually get infinitely far away from dog2. Accordingly, if A is greater than 1, then the equation has a finite value when x equals 1, the intersection point. If A is less than 1, then the equation has an asymptote. As A gets very close to 1, regardless of whether it is larger or smaller than 1, the graph dog2 takes gets ever so close to what it would take if A were 1. For me, I think this kind of reminds me of the nature of, well, the natural logarithm. What we all learned first as an inverse exponential function with an irrational base is, in fact, a limit of a power of x. Personally, the dog problem was a nice way to experiment around with I and calculus, other than stupid partial fractions. The hackneyed quote-unquote going into the unknown was quite an adventure. I hope that you guys also can take away a little bit of enlightenment. Solving and understanding something, whether it's an abstract math problem, a poetry analysis, an everyday problem in the bathroom, or an engineering challenge, is really a blessed feeling to get. So go out there and do something, bro. This is kind of cringe, not gonna lie.